Okay, so we have made it to our final set of identities. These are called the double angle and the half angle identities. These are going to work a lot more like formulas, kind of like the sum and difference formulas. They're not really used to do the verification of identities the way that the other ones are all that much. Maybe some of the super basic ones are. If you took AP Pre-Cal last year, we learned 2 of the various ones of these, which I know you've forgotten since then, and that's okay. Our double angle identities are all right here. Double angle means that it is multiplied by 2 inside the function itself. So if you see cosine of 2 times alpha or theta or x, or sine of 2x, or tangent of 2x, that's when you're using these formulas. Or for the half angle identities, it's kind of vice versa, if you're taking half of an angle from inside the sine, the cosine, or the tangent, that's when you're going to use one of these. Now there's a lot of choices when it comes to half angle and double angle identities. The double angle identity for cosine has 3 options. So your job sometimes when you're using it is to pick the one that makes the most sense. If you have another cosine squared of alpha, maybe choose this one so that you can combine like terms. If you have another sine squared of a, maybe choose this one because then you can combine some stuff together. Same thing here and here, you just have one choice. Down here for all of the half angle identities, you at least have 2 choices because this is not choose both, this is either plus the square root or minus the square root. So unlike these symbols, this one is choose one. You have 3 choices though for tangent. What's nice about the half angle identities is because these are a little bit confusing, the instructions usually tell you which one to use. It's really going to come down to you to choose the right one on the double angle, but the half angle will kind of give you a hint on what to use. Let's see what one of these looks like in real life. On example 1 for our double angle identity, it says that if you were given cosine of theta being equal to 3 over 5 and that sine of theta is less than 0, we want to find sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. So we're going to use all 3 identities, double angle identities for sine, cosine, and tangent to do this. I know from doing this problem ahead of time that when we use this, we're going to need to know the sine, the cosine, and the tangent of this angle, which means I need to know more than just the cosine being equal to 3 over 5. I need to know the x, y, and r like we did last time. If they gave us that cosine is 3 over 5, which two of those 3 letters did they give us? R and no, x. So that means that the x is 3 and that the r is 5. Do you remember the Pythagorean triple here? 4. Now, is that 4 going to be positive 4 or negative 4? Is it going to be positive or negative?
Oh,
Negative. If it's less than 0, that means it has to be less than 0. Okay, so if we go in here, this is like our little sidebar, so we can use these values later. If we wanted to do the sine of 2 theta, we know from the formula on the formula chart for the double angle identity that sine of 2 theta is equal to 2 times the sine of theta times the cosine of theta. Good thing we found all these values because now that we know x, y, and r, we can substitute those in using the chapter 1 formulas for each of these. Sine is always y over r. Cosine is always x over r. Top times top, bottom times bottom. And to make this even easier on you, I'm going to change this number 2 that's in the very front to the fraction 2 over 1, just so it matches. Now we can do all tops times all tops and all bottoms times all bottoms. 2 times negative 4 times 3 is negative 6. Nope, negative. What is negative 2 times negative 4?
Negative 2.
Why is my brain 8? Oh my gosh. Hello, welcome to the party. Times 3, that's negative 24.
Wednesday.
I know. Ignore me. 1 times 5 times 5. Actually, don't ignore me. I'm trying to teach you things. 25. And boom, that's it. That is the sine of 2 theta. So we want to use these double angle identities to be able to use regular sine, cosine, and tangents and not the double angle so that we can use x, y, and r. if we continue doing this, this question wants all three. So we do cosine of 2 theta. Honestly, we get to pick whichever one we want. But just for practice with squaring stuff, we're going to pick the first one. The formula for cosine of 2 theta is cosine squared of theta minus sine squared of theta. So if I plug in what I know, cosine is 3 over 5. I have to make sure I square that whole thing. So I put that square on the outside of parentheses. And then I'm going to subtract negative 4 over 5, but I'm also going to square that. So again, squared. What's the rule when you're squaring a fraction? Square both. So we'll go ahead and do that over here. That means this is 9 over 25 minus 16 over 25. Luckily, these have a common denominator, so we can subtract them. 9 minus 16 is negative 7 over 25. That's the value of 2 times the angle theta. And then last but not least, we're going to do the tangent of 2 theta. If we look at the formula for tangent of the double angle for theta, the formula says that this is 2 times the tangent of theta over 1 minus the tangent squared of theta. These are all derived, by the way, from your sum and difference formulas. I didn't make you derive them, but it's actually very interesting how we got these formulas. I figured you didn't, which is why we're just using them. So if we go ahead and plug stuff in, we're going to have fractions and fractions, and I know that that's just like a little bitty spot. I'm so sorry. What is the tangent of theta? Well, tangent is defined to be what over what? Y over x. So this is negative 4 over 3. So I'm going to use that fraction twice, but the second time I'm going to square it in the bottom. For the numerator, top times top, bottom times bottom gets me negative 8 over 3. I'm going to square that fraction first. This becomes 1 minus 16 over 9. But to save space here, I can't subtract 1 and 16 over 9 until I change 1 into what fraction? 9 over 9. We want them to have the same denominator. Well, 9 minus 16 over 9 is negative 7 over 9. What do we do when we're dividing fractions? Ooh, if there's one thing you learned from me this year, it is keep, change, flip, isn't it? Something's wrong. What did I do wrong here? Nope. Trust the process, Ms. Quigley. You're right. Let's go ahead and multiply. Negative 8 times 9 is negative 72. 3 times negative 7 is negative 21. It sure can be reduced. First of all, negative divided by negative is positive. 72 and 21 are both divisible by 3. 72 divided by 3 is 24, and 21 divided by 3 is 7, which is totally a question you could ask a calculator once you get there. This sort of feels like the panic set in. This is the moment the panic set in last class, is what I'm trying to say. When we did the sum and difference formulas and I started plugging in x, y's, and r's, we all panicked. Does this feel a little more accessible? Which means we can go back and we don't have to panic on the other one. That's what we did there. We just had to do x, y, and r usually for 2 angles because we needed an alpha and a beta angle. This one we only needed 1 angle. So we only had to do the x, y, and r one time. What we can also do is find the values of all 6 trig functions, not just sines, cosines, and tangents. Example 2 says find the values of the 6 trigonometric functions of theta if cosine of 2 theta is equal to 4 over 5 between 90 degrees and 180 degrees. What quadrant am I in, by the way, between 90 and 180 degrees? Quadrant 2. So that's just a good note for yourself. That way we can remember what should be positive and what should be negative later. So interesting. We were already given the double angle. We were told that the cosine of 2 theta is equal to 4 over 5. I also know that the cosine of 2 theta has, where am I trying to go here? Formula. Wow. Oh my gosh, I promise I'm awake today. Let's use the second formula on our formula sheet for the cosine of 2 theta. The cosine of 2 theta, based on the second formula, is 2 times the cosine squared of theta minus 1. The reason I chose this one instead of the first one is that it only uses one trig function instead of both sines and cosines. I could have picked the third one for a similar reason. It only uses one. Let's start solving for theta. Specifically ignoring, don't mark this part out, but if you're like, what are we solving? We're pretending like this part doesn't exist. And we just have 4 over 5 equal to 2 cosine squared of theta minus 1. If I'm trying to get theta by itself, I'd have to add what to both sides? 1. To write 1 as a fraction where I can actually add it with 4/5, how would you write it? And what is 4 over 5 plus 5 over 5? 9 over 5. Look at that fraction math we just did in our head. Whoa. How do you get that cosine squared of theta by itself? Divide by 2. When I divide by 2 on both sides, I end up with 9 over 10 times the cosine, what, equals cosine squared of theta? And then we square root. Whoa, what do we do when we square root things? What do you have to put in front of it? Plus or minus. So we have plus or minus 9 over 10 equal to cosine of theta. Interesting. Not super helpful until we do the following. In quadrant 2, is cosine positive or negative?
No, negative.
Negative, because quadrant 2 is the S quadrant, so only sign is positive. So that means that I'm going to drop the plus sign. I'm not going to use it. I'm just going to use the minus sign. And I'm going to do the square root of both the top and the bottom. What is the square root of 9? What is the square root of 10? Something, right? Now, don't let your spidey senses go haywire.
Yes.
Because what are you not allowed to have in a denominator? Okay, don't love it. But right now, what we need out of this, because that's not where we're answering, we need x, y, and r. If you got here, where cosine of theta is equal to these two things, what is negative 3? Is it x, y, or r? It's x. What is square root of 10? R. We need that information. And now, this is not a Pythagorean triple, so we do have to actually show some work to find y. What do we do to find y? Yeah, Pythagorean theorem is kind of ugly. So we're going to do square root of 10 squared minus negative 3 squared. Starts off real ugly and then gets real cute real fast because square root 10 squared is just 10. And negative 3 squared is what? 9. 10 minus 9 is 1, and the square root of 1 is 1. So we have that y is 1. Now, what was the point of this question? So glad you asked. I want all 6 trig functions. I want the values. So if you have x, y, and r, you can give me all 6. I'm going to change colors because I already wrote a lot right here. Sine of theta is y over r. It would be 1 over square root 10. But how would you rewrite that? Cosine of theta would be negative 3 over square root 10. But how do you rewrite that? Negative 3 square root 10 over 10. Tangent of theta is y over r. Y over x. Do I have to do anything with that one? There's the first 3. What are the other 3?
It's the inverse.
Yes, so cosecant of theta would be square root of 10 over 1, or square root of 10. Secant of theta would be square root of 10 over negative 3. And cotangent of theta it would be negative 3 over 1. Once you have x, y, and r, whatever it takes to get them. In the first problem, we were given enough information to start at x, y, and r. In the second problem, we had to solve, we had to solve cosine of that double angle to be able to get x, y, and r. I got it to stick, there we go. And then we have all 6 trig functions. Never forget those formulas I made you tell me every day last quarter. One of the things I would like for you to get comfortable with these identities is using them, maybe not necessarily in a verification of an identity, but to simplify other expressions. Do you notice that this right here looks like that cosine function, double angle identity for cosine? If you look at that, cosine of 2a is equal to cosine squared of a minus sine squared of a. Like that looks like that pattern. The only thing is that a is 7x. So we're gonna substitute this just to make this easy for ourselves. Mathematically, this is technically called a u substitution, so we should be using u. But since a is on our formula sheet, we're going to let this be a, which means that I can substitute out 7x and substitute in a in its spot. And immediately, I really see that this is the formula from my formula chart, which is the cosine of 2a. But what is a one more time? 7x. So if I put that back real quick, this actually becomes the cosine of 14x. That's the simplified version of where we started. That's it. So if you recognize the formulas, maybe it has some extra stuff in it. Just take that extra stuff out for a hot second, fix it, make it look right, and then put your stuff back in. It's called a u substitution, even though we used the letter a. This next one's kind of interesting because it doesn't quite look right. Okay, I'm going to get us started. I'm going to let a be equal to 15 degrees. And if I substitute that out, just like I did in problem A, we'd have sine of A times the cosine of A. Is that anywhere on the double angle identity formula chart? It is? No, but it looks like one. Which one does it almost look like? We're missing a 2 in front of it. Let's put it there.
Oh, okay.
But you can't just like slap a 2 in front of it because you're changing the problem. Like when you're changing and making things have a common denominator, you can multiply by the number 1, which means I could multiply this by 2 over 2. What is 2 over 2? 1. So I'm multiplying it by 1. But I'm going to like split this apart a little bit, and I'm going to write this as 1/2 and then 2 sine of A cosine of A. Do you see how I just took the 2 from the top? Oop. Now this little middle part right here, I'm going to put it in parentheses just for good measure. Is that from my formula chart?
Yeah.
Yeah, in my formula chart, that is 1/2 sine of 2 times A. Now that I've gotten it back, let's put the 15 degrees back in. This is going to be 1/2 sine of 2 times 15 degrees, which is 1/2, what? 1/2 sine of 30 degrees. And just because I can't help myself, what is the sine of 30 degrees?
That's a great question.
Who's got their unit circle out and ready?
That's 30 degrees, you said?
Yep.
1/2.
1/2. So then I have 1/2 times 1/2. This really simplifies down
12.
to a 1/4. Yes, sir. Yes. So you noticed that this was close, but not quite, or I guess when we were here, close, but not quite the formula from the formula chart. We needed a 2 in front of it. You can manipulate equations by multiplying by a scalar of 1 without changing anything about it. 2 over 2 is equal to 1, yes?
Yeah.
So I'm just going to take this fraction apart. I'm going to put the 2 here, and then I'm going to put the 1/2 in front. Why a 1? You can't have just a blank denominator. A blank numerator, I guess. right? Because what is 1/2 times 2? 2 over 2, which is 1. I've still just multiplied by 1, but I'm writing it so that I see exactly what's on my formula chart. This is exactly on my formula chart, and identity is sine of 2a. Then we just put the a back. A was 15 degrees. 2 times 15 degrees is 30. Couldn't help myself because 30 degrees is something we know. Sine of 30 degrees is 1/2. 1/2 times 1/2 is 1/4.
And if we don't know, like, it doesn't give us the...
Yeah, if this happened to be like sine of 80 degrees, we don't know sine of 80 degrees on our unit circle, you would have stopped here. Or if there was a variable left like this, maybe it said 30x, you would stop. But if it's something we know, I can't help myself. Use that unit circle.
Oh, you can.
No, I really can't. My too much gene kicks in and I just do too much. Do y'all want to just wait till after lunch for the back?
Yes.
Okay. Example 5 wants us to find the exact value of cosine of 15 degrees, but using the half angle identity for cosine. Obviously, finding the exact value of cosine of 15 degrees is potentially something we did last class, because you can find this by doing 45 degrees minus 30 degrees, but we will get a numerically equal but different representation of that value, that exact value, if we use the the half angle formula. So yeah, we're going to basically do what we did last time and find the exact value of cosine of 15 degrees, which we did doing 45 minus 30, so it was the difference of cosines. However, we're going to use the half angle identity for cosine, meaning we're going to do the following. Cosine of 15 degrees. We know that the cosine of 15 degrees has a formula, if we're using the half angle formula, that says we're either going to choose plus or minus the square root of 1 plus cosine of angle A over 2. Notice I didn't put an actual angle there yet, because we actually have to figure out what the angle is. It's not hard to do this, but remember, since we're using the half angle identity, we're going to say that this 15 degrees is A divided by 2. In which case, what is A? 30 degrees. So I know that that means then 30 degrees goes inside the formula. The only other thing we're going to do before we really get too far is make the choice of whether we're doing positive or negative. If the angle A is 30 degrees, what quadrant is 30 degrees in? Quadrant 1. Is cosine positive or negative in quadrant 1? Positive. So we can erase the minus sign, and really the plus sign, right? We don't need it. Because we know that in this quadrant, cosine is going to be negative. Positive. So cosine is positive. Okay, cool. So we've made a couple choices here at the beginning. We know that the angle A we're using is 30, since half of it would be 15, and that we're using the positive square root because that's quadrant 1. Let's go ahead and start doing what we know. Those of you who have your unit circle out, what is the cosine of 30 degrees? Square root of 3 over 2. So if I start doing this problem, good catch, we would do the square root of 1 plus square root of 3 over 2 divided by 2. No, not quite. We can, though, separate this number that's underneath the square root, separate the fraction into two numbers having the same denominator, meaning this would be like 1/2 and then square root of 3 over 2, which is over 4. If you'll let me take that shortcut. Oh, but now I need to add two things together. What do they have to be able to add them together? The same denominator. I'm going to go sideways just to save some room here. This is going to be 2 over 4 plus square root of 2 over 4. Yep, thank you so much. I knew that looked weird. I know. Okay, well, we can add those two things together. This ends up being the square root of 2 plus square root 3 over 4. And then if you're taking the square root of a fraction, you can do the square root of the top and the square root of the bottom. And what is the square root of 4? 2. And we're done. That's it. Yes.
So, did these not cancel out at all?
No, but they combined together in a different way. They didn't cancel, they combined. So here, I pulled this apart at the plus sign, so it's 1 over 2 and square root of 3 over 2 over 2, but that's just square root of 3 over 4. Then to add these two numbers together, they would have to have a common denominator now that I don't have fractions and fractions. Common denominator, one term, adding them together, square root top and bottom.
But was it the same number?
Like you're talking about this one and this one? Well, this 2 is stuck underneath that square root. Can't go inside a square root from outside a square root.
So why can't you simplify that 2 to that? Couldn't you just square root of 3 over 2?
No, because this denominator goes to both terms, so could go back here, and the only way you can reduce this is the first one. So we would just go in this circular movement. So you want to split, common denominator, add square root of both sides, top and bottom.
But like we shouldn't touch to begin with a fraction.
Say again?
The square root of 3 over 2 divided by 2. We shouldn't be able to touch that at all because it's a fraction.
But it's all underneath a square root. You can't touch this 3 because it's underneath a square root, but this whole thing is underneath a square root together. If this divide by 2 was outside the square root, we'd be done. Can we try another one just with some gnarly algebra?
We have choice.
No, we're going to do it anyways. Okay, find the exact value of tangent of 22.5 degrees using the identity. Look, I even told you which one to use. Tangent of a over 2 equal to sine of a over 1 plus cosine of a. Okay, let's do what we did before. We know that this tangent of 22.5 degrees will be equal to sine of some angle over 1 plus the cosine of some angle. What is the angle I'm going to use? It will be A. So if A over 2 is 22.5 degrees, Joseph already said it, what is A? 45 degrees. So I can put that angle in here. Bonus question, even though we don't really need this for this one because we don't have to make a choice with that square root, would this be in quadrant? Okay, yeah, quadrant 1. I'm seeing everybody. So quadrant 1, so everything is positive. Okay, we're good to go. Cool. Unit circle moment. What is the sine of 45 degrees?
Square root 2 over 2.
What is the cosine of 45 degrees?
Square root 2 over 2.
Oh boy. Here comes the algebra.
Oh no.
That was the trig. Here's the algebra. First things first, let's get that denominator to have a common thing so we only have one fraction in the denominator.
Okay.
I'm going to do this kind of quickly, meaning I'm going to erase the 1 and I'm going to rewrite it as what? 2 over 2. That's just easier than rewriting the whole thing, and I didn't do much there. Okay, so I can add that denominator in the bottom to, it becomes 2 plus square root 2 over 2.
So they combined that.
They combine together. Ah, I'm dividing fractions.
Ah.
What are the rules?
Change flip.
Keep, change, flip. So I'm going to keep, I'm going to change, I'm going to flip. Anybody spidey senses going off? I know there's a lot of 2's floating around, but specifically, there's a 2 on top, and there's a 2 on bottom. What can I do? Cancel. So I end up with square root of 2 over 2 plus square root of 2. Yes. So to finish this one off, following the algebra rules we've learned, to rationalize this denominator, you have to multiply by the conjugate of that denominator. I don't know. It's a random playlist I found. I'm going to go ahead and draw arrows here because I feel like the questions people have asked me have all come from me foiling too quickly and not showing my work. Which means if I'm doing this, I'm going to multiply. This ends up being 2 square root 2 minus 2. Do we follow?
Yes.
Square root of 2 times square root of 2 is 2. In the bottom, I'm going to FOIL. I actually am not going to draw the arrows. I already take that back, but I'll point at the arrows. 2 times 2 is 4. 2 times negative square root 2, negative 2 square root of 2. Square root of 2 times 2.
Positive 2 square root 2.
Nice. And then we have square root of 2 times negative square root of 2.
And -2.
Negative 2.
And then don't the two, the positive and negative cancel?
Correct.
Can we just use no.
It is the difference of 2 squares, yes. Square the first, square the second. Subtract them. What is 4 minus 2, though? Because that's the only thing I have left on the bottom.
2.
2. So I have 2 square root of 2 minus 2 over 2. Whoa.
That's 2, miss.
That's a lot of 2's.
2. Okay.
The only way you can cancel stuff out is if it's multiplied. But we can make this work here. What do both terms in only the top have in common? 2. So I can factor out that 2, and I'd be left with square root 2 minus 1. Now do you see that those 2's are by themselves?
Yeah.
Not added or subtracted to something, but multiplied only on their side.
Now we can cancel.
Now we can cancel, and we're left with square root 2 minus 1. Here's the thing I want you to realize. This step was the trig. These
All
steps are
that-
the algebra.
How many questions like this round?
There's only 20 questions total, right?
30 questions.
4, but for tangent only 2.
Wait, how many questions are on this?
On the test, there's 20.
Close.
Are you getting a curve?
Where's my shirt go?
Probably.
Is there any multi-question?
No. Okay. So the part of these last 2 lessons that are hard is not trig, it's algebra. We can do algebra.
Can we?
You can.
The trig?
Yes.
No.
The trig is like the, and then the algebra is the.
Yeah, but
Is trig just like putting it, like following the instructions and then?
Yes, this is also how calculus works. You do this step of calculus and you do this much of algebra. Algebra is the basis of everything.
So I'm never taking calculus.
That's why we take college algebra before we take these courses.
So I'm not taking calculus.
You're taking trig, you're doing the same thing.
The trig stuff makes the algebra stuff look way easier.
Trig is,
was like it's super complicated, and the algebra it was complicated last semester. But now it's
well, that's great. That's what I want to hear. That means we've learned stuff.
No, that means I'm going to go back to algebra.
Oh, I have this on.